solids, they're all composed of atoms or molecules arranged in a specific way. They can be crystalline, in other words, they form a particular kind of a structure, or they can be what's called amorphous, which is more like longer chains, okay, that don't fit together very well. They just sort of lay like pieces of spaghetti, you know, on each other. And let me see. I have a newspaper here, so I could, no, okay. I think this paper will work. But okay, let me see. For example, when you make paper, I'll try it, see if it'll work. When you make paper, I'm going to assume paper is made up of these amorphous chains. But you can align them by when you're, see, this is in a solution, a cellulose in a solution, and as it's drying and it's pulled on rollers, they stretch it a little bit. And if I had newspaper here, it'd be easier to show, because this works really well, and some of you may already know how newspapers are sometimes very hard to tear, all right? But let's see, I'm assuming now that it's going to be aligned in this direction, it's been pulled this way, and if that's the case, I should be able to tear a straight line down here. Let's see. Well, that's pretty good, right? But now, if you try that sideways, this is probably too small. Let me try it this way. Where now, again, we're pulling it this way, so the chains are not aligned so well. They're now tougher to get through here because they've been, you know, in this direction, they're not so aligned. So if I try to tear it here, well, it's still not too bad. It's a little bit. In a newspaper, you'd find out that you couldn't tear it this way at all. Okay, you'd have to get scissors. Okay, but you could tear it the long way. Okay, top to bottom. But that just shows you how the cellulose molecules are aligned with each other and pulled to be sort of like this. Okay, let's see. The specific gravity of a material is just equal to the mass of the material divided by the mass of an equal volume of water. I just want you to know that, you know, so if you see that term, then, you know, you won't see it on the test, all right? But in case you see that term, I just want you to know what it means. It's comparing the mass of a certain mass of the material to an equal volume in mass of water to it. That's called the specific gravity. So, like it says here, if a substance was 3 times as much as much of an equal volume of water, in other words, if its mass was 3 times as much, or as I said there, weighs 3 times as much, you'd say specific gravity was 3. It's all relative to water where you see that word specific gravity. And some of you may see that in some of the work that you may be doing in the future. Okay, so, and there's a table in your book that goes along with this, but, okay, now let's talk about compression and tension. If you have a bar of material and you put it, and you have it suspended between 2 points, and you put a weight on it up here, what's going to happen is, in the area up closer to where the weight is, closer to the top, the molecules there are going to be compressed together, whereas the molecules on the bottom are going to be pulled apart, okay, as this thing bends. That's how it has to, you know, can you see how that actually happens? I just use this to point out to you how, if you were looking at this from this direction here, how in the center you really don't need to have a lot of strength. This is why they use things called I-beams in construction. You know, you might wonder, why is it an I-beam? Why does it look like that? Why isn't it a solid beam? It's not a solid beam because you don't need to have all this extra weight out here for strength. The strength is completely supported by the center bar here. So in any case, I just wanted to point that out to you, the difference between, you know, or rather where these I-beams come from, that's all. So if you want a reference on that, you know, I just want you to understand that it's just as strong as if that were a solid bar, okay? It's just the same strength in terms of supporting it on something like this, supporting it in a couple of places and putting weight on it. Okay, scaling. Now in scaling things, you have to be careful about that. You can't just scale things up. And I used to have a video that worked with this, but it's unfortunately it's a video cassette. We don't use those recorders anymore. So I can't show you the nice story about this or a nice explanation of this. But if you had a little scale, or let's say you had a cube that was like 1 centimeter by 1 centimeter by 1 centimeter, you guys can see that the volume is going to be 1 times 1 times 1, or 1 cubic centimeter, okay? But the area is going to be 1, all right, times 1, right, to get the area of a face. And then there are 6 faces on a die, right? There are going to be 6 faces on that. So it would be 1 times 1 times 6, or you would have an area of 6. And the volume to the area, the ratio is going to be 1 over 6. The volume, 1 cubic centimeter, the area, 6 centimeters squared, for example. But now if you double this, so that you have 2 here and 2 there and 2 going up, now you see what happens is the volume is now 2 times 2 times 2, or it's going to be 8, right? 2 times 2 is 4, times 2 is 8. All right, so you now have a volume of 8, but the area is going to be 2 times 2, which is 4, but there are 6 sides, so it'll be 4 times 6, or 24. So now your volume over the area is going to be 8 over 24, or 1 over 3. And you know, if I had the video, you guys would see he does this for a whole bunch of different sizes, and but you always come up with the same, just to strengthen the same answer here, and that is, as something gets larger, all right, then I want you to realize that as the volume of something increases, the amount of surface area that you have decreases. You see, we had a ratio of 1 volume to 6 here. Now, when we double this, it's a 1 volume to 3. Okay, in other words, you have a lot more volume than you do surface area. All right, and this is really because the surface area is related to the square of the sides, whereas the volume is related to the cube of it. But this is why I think I have it on another slide here. If you worked in a restaurant, let's say, and you worked in the kitchen, and you went to work one day, and you got in there, and they said, let's say Peter was working in the restaurant, and he got there, and they said, "Oh, Peter, good, you're here ahead of Raheem, and I have something for you to do. You guys have to peel this 50 pounds of potatoes. Now, I have 50 pounds of potatoes, large potatoes, and 50 pounds of potatoes that are small potatoes. All right? Since you're here first, Peter, which ones would you choose? The large potatoes or the small?"
Large.
Large, right? Don't you all see that? You'll have less skin when you get done. Do you all see that? That's because of this relationship between volume and, God bless you, volume and area. Okay, you'll have a lot less skin left over, a lot less work. Okay, so, okay. Anyway, that was the whole point of this. I just want you to realize when you scale things up, you have to be careful. In the video, he does an example of, let's see, he shows an X-ray of a leg of an elephant versus an X-ray of the leg of a cat. And of course, you guys can just imagine how much thinner the bones are in the leg of a cat as compared to the elephant. But his point being, if you scale this up, if you made the cat as big as an elephant, it wouldn't be able to stand up because its bones wouldn't be strong enough, because they wouldn't be able to get enough area to support that amount of weight that's above it. It wouldn't happen. In other words, the volume is increased, but the area is not increased enough. Or he did another example about if an ant can carry so many times its own weight, but if you scaled an ant up to the size of an elephant, the ant would just collapse. It wouldn't be able to stand. Even King Kong, a gorilla that big wouldn't be able to stand up unless you thicken the legs, okay, of the gorilla, so that it could stand that weight. When people build bridges, for example, they might build a beautiful model of a bridge here, but of what they want to build, but they can't just scale that up and, you know, get all those same measurements and make the bridge. It'll collapse. You have to take into account the additional weight and the fact that you have more area that you're going to need to support the weight that is above it. But anyway, I'm going too long on that. I don't need to go so long. Okay, here is another area. We did the 1 to 3, and here, just to give an example of a 4 by 4, okay, the volume will be 4 by 4 by 4, 4 times 4 times 4, which is going to be 64, and it's going to be over 4 times 4, which is 16 times 6, or 96, and now it's only 1 over 1.5. Again, the point being that as something increases in volume, all right, the surface doesn't keep pace with it. All right, the surface is much less, which gets back to the this potatoes thing, this potato question that's here. That the larger potatoes will have, maybe a way to look at it is there's more of the meat of the potato and less of the skin as it gets bigger and bigger. So that's all on scaling though, I just wanted to go over that. Okay, liquids. That's enough for solids. Now for liquids, as you guys know, the molecules in a liquid can slide around one another, but I want to point out to you that, remember we had that the pressure is the force divided by the area. Well, in this case, the pressure in the liquid here is going to be equal to the weight of the liquid above you divided by the area of the bottom of the container. Or like in our case, the air pressure that we feel here on the Earth is due to the weight of all the molecules that go up the roughly 20 miles to get to outer space. That's all it is, you know, to outer space, 20 miles. You know, I mean, think about how easily you drive 20 miles, right? That's how thick the atmosphere is. It's very thin. Our atmosphere is thinner than the skin on an apple, okay? It's very, very thin, but in it, which is why we have to protect it. But in any case, it's the weight of all those molecules, gravity pulling them down, pressing on us, that gives us the air pressure that we feel down here. So I just wanted you to realize that. We're going to talk now about liquids, though, and some of the aspects of liquids that, that pertain to pressure. Blaise Pascal was the guy who came up with it. He came up with some pretty important things, but here was one of them. He said the pressure in a liquid is equal to, first of all, how dense is it? The more dense it is, then the heavier it is, right? But then you multiply that by gravity, and then it's just related directly to the depth. And you guys know that. You dive in a swimming pool or something right as soon as you get down, where you can feel that pressure building up. That's from the water above you, increasing the pressure. Same thing. Well, what Pascal showed with this formula, he just said, well, the pressure, if you have a reservoir, the pressure down at 5 meters is going to be equal to the density of water times 10 times 5, right, which is going to be the density. The density of water is I'm using 1 here, but it's going to be 50. And then if you go down another 5 meters, so now you're down 10 meters, you can see now the pressure is 100 units. And if you go down 15, it's now going to be 100. You guys see there's a direct relationship there. This is why when they build dams, all right, at the top of the dam, it doesn't have to be thick at all, because there's only a little bit of water to give you pressure against the side of the dam. But the deeper you go, the more pressure there is, and that's why when they build dams, they will build them like on a slope, so that they're a lot thicker down at the bottom than they are at the top. This also explains what happens. You guys have probably seen this at one point or another in your life, probably by accident, but if you have a can that has several holes in it, and as you go up the can, several holes, and you fill that with water, I think you guys know that the water that comes out of the highest opening will actually come out the slowest, right, and fall more quickly, whereas at the bottom will come out farthest, and that's just because of different pressure. Okay? Right, does that make sense? That's Pascal's law for the pressure of a liquid. Okay, then, now in the textbook, I just wanted to point out to you there were a couple of things that they explained or drew a lot better than I could. Let's see, if you look at page 145, they have a patient. In this case, I just want you to realize that when you look at that figure on page 145, it doesn't matter where the hose, rather where the tubing goes. It doesn't matter, okay? The only thing that counts in terms of the pressure of the fluid going into the patient is the height of the fluid. compared to the where it's going into the patient's body. All right, that's going to determine the the pressure. I think you guys probably know this. You've probably done experiments or worked with patients before, and you know that if you raise the IV bag or the IV bottle, how you'll get more pressure, to push the fluid into the patient. But again, this just goes right along with what we had up there about Pascal. All right, just that it's only the height that makes a difference. Then on page 146, how you fill up an eyedropper. The point there is you are lowering the pressure in the eyedropper. Okay, you can see in the top that you have the eyedropper into the solution. Then what they'll do is they'll squeeze the bulb on the end and squeeze out the air, some of the air that's in there. And then when they release their hand from that, what happens is then there's a lower pressure inside that eyedropper, and that is what allows the fluid to go in. But what's actually happening to the fluid is it's getting pushed in by atmospheric pressure. It's pushing on the surface. Okay, you have now lowered the pressure. Let's say you had a straw and you were drinking a soda. When you suck on that straw, all you're doing is lowering the pressure in the straw, so that now that same air pressure that's pressing on the outside will allow the fluid to fill up the straw so you can drink. That's also why if the bottle is sealed, the straw won't work. You can try that sometime, just convince yourself. You need to have that atmospheric pressure pushing down on it. Let's see, and then 149, this is a manometer. Have you guys all used the manometer at one point or another in some of your studies, some of your lab work? No, it's very old-fashioned. It's very old-fashioned. But the thing about the manometer is when the pressures on either side of that U-tube are equal, then the levels of the mercury are going to be equal. But then if you lower the pressure, say on one side, what will happen is the mercury will change its height, right? Like they show you in the picture here. You see, and that difference in height can be related directly to the amount of pressure that you're experiencing. And okay, and pressure is a peculiar thing, because depending on what career you guys go into, if pressure is involved in it, and the measurement of any pressure, it's liable to be very different. Okay, if you're going to be measuring body pressure in the body, you'll be dealing with millimeters of mercury. If you're measuring the pressure in an angioplasty balloon, it'll be in what are called bars or atmospheres. Okay, and you'll just be using different units of pressure. If you're looking at, if you're taking your car in to have work done on it, and they're putting air in your tires, in this country they still use the British system. It'll be pounds per square inch. Right? Your car probably says, if you look in the door, when you open the door, look in the frame, it'll tell you how many PSI or pounds per square inch you need to have in the tires when they're just at room temperature. And of course, nowadays they also have the international unit, kilopascals. But we'll talk about pascals in a minute. That's the international unit for pressure. Well, you guys have probably experienced this too. Whenever you've gone in an airplane, when the plane takes off, and somewhere between 5,000 and 10,000 feet off the ground, I remember asking a friend of mine who's a pilot, I said, when do you guys lower the air pressure in the plane? He said, I don't know. He said, I used to know. He said, but it's done automatically now by the electronics on the plane. But it's between 5,000 and 10,000 feet somewhere. They'll lower the pressure. Because when the plane gets up high, the air pressure outside is so low, they don't want to have a large difference in pressure between the inside and the outside. So what they'll do is they lower the pressure inside the plane so it has less of a chance of blowing a window out, okay, when you're higher up. So what they do is they lower that pressure in the plane. And when the plane comes in for a landing, you get down around that 10,000 or so feet, and now automatically the air pressure is restored to normal. All right, well, what happens with our bodies, though, is you guys know we have an eardrum, we have the middle ear. You guys have studied all this at some point, so that's why I'm not belaboring it. But The thing is, you have that middle ear, a little sealed area inside your ear, the middle ear, and it has a tiny tube that goes to the back of your throat called the eustachian tube. So if you now, when the pilot lowers the pressure, when you get up, say, at around that 7,000 feet, they lower the pressure, now you have too much pressure in that middle ear. But what happens is and so it makes your eardrum bulge out a little bit, but what happens is your body just easily allows that excess air to flow into the back of your throat, okay? And now you're normal again. The opposite happens though when the plane is now restoring air pressure. So now what happens is your eardrum will bend the other way, flex the other way, but now you have to get air up through that eustachian tube back up into your middle ear, and that sometimes is hard. Especially if you're congested, okay, you probably have experienced that. I know I have when I've flown sometimes, no matter how much, sinus medicine I take or whatever, if I'm really not well. When that plane comes in for a landing, sometimes I can't hear or certainly can't hear normally for a few minutes after the plane gets down. You might have experienced that too. But all that's happening here is you need to get air to go back into the middle ear. That's why they tell you to move your jaws and, to try and get air to go through those two little eustachian tubes back up into your ear. Okay, just a little practical aside. You guys all understand that? Right? If I ask you that in the test, you can figure that out? Okay. All right. Let's see. Buoyancy. Gee, that's it for... I'm going to come back to Pascal, I think, but all right. Buoyancy, okay? Buoyancy is, as it says, the loss of weight when an object is placed in a liquid. You've all probably experienced this. So you notice you can lift up something that's relatively heavy when it's underwater, all right? But when you get it out in the air, now you've got to deal with its real weight. But there's an additional force that's in the up direction that is lightening the object when it's underwater, right? You guys, this makes sense? You guys have experienced this at some point? Okay. I remember once I was visiting somebody here in Fort Myers. They had a condo, and they build all these condos on these little lakes. They sort of surround the lake so that people can sit out on their lanais and have a nice view of the lake. And they put bass and things in the lake, which is nice for people to fish and so forth. Well, one day I was visiting somebody who lives in a place like that, and I was out on the lanai, and I heard all this splashing going on in the water. I thought, what is that? I went to the edge and I looked, down at the little pond, that little lake that's there, and there was a cormorant. You guys know what a cormorant is? It's one of the birds that dries its wings. The anhinga has a pointed beak and it spears fish. The cormorant has a beak like a seagull, and it grabs fish, okay, with the beak. But in any case, it was a cormorant, and it had grabbed a little fish, not so little actually. And what would happen is the cormorant, when he's underwater grabbing that fish, he can move that fish anywhere he wanted, right? But when he tried to fly out of the water to go onto land or onto a tree to eat the fish was too heavy, and he'd fall back down in the water. And then he'd thrash around a little bit and try and fly again and fall back in the water. See, he didn't know this buoyancy, this Archimedes principle about, he didn't know that. He eventually let the fish go. It was just too big a meal for him, but he couldn't carry it out of the water. So the thing that about buoyancy that Archimedes figured out was, he figured out the size of that force that's pushing up, that's helping you to lift something if it's underwater or to make it lighter. The size of that force is exactly equal to the volume of water, the weight really of the volume of water that object has displaced. So if that object, had a volume of, let's say, 10 cc's, all right, of an object, when you put that in the water, it displaces 10 cc's of water. And in doing that, what happens is that value of the weight of that 10 cc's of water is what gives you this buoyant force pushing up. The weight of the object hasn't changed. Gravity hasn't changed. The object still weighs the same, but now it has that additional upward force that's holding the object up. But he figured out exactly mathematically, I mean, with numbers and all, he figured out exactly what that was. And, you know, if we were to take the real physics course, you know, where you have all the math in it and all, we could figure out how Archimedes used that fact to tell the king that, no, that crown that you're being sold as being gold is not all gold, it's actually only partially gold. And, you know, there are a lot of stories like that where he used this fact to figure out, because he knew with gold exactly how much the object should weigh in water. And when it doesn't weigh that much, he knows there's something else in there besides gold. Maybe they diluted the gold a little bit with tin. But in any case, this buoyant force is equal to the weight of the water that's displaced. If the object's weight is greater than the buoyant force, it sinks. If it's less than the buoyant force, it floats. Okay? Makes sense? Because you've got these two competing forces here. More weight, less weight, or the same weight before you start? What do you think? Same. Same, right? That's what you would think. Right? It's wrong, though. It will show more weight. I wish we could do that. You guys that have the lab will have to remind me this week or next week. Let's do that so you can see it. Because what's happening is you're fooling the scale. The scale thinks that there's water there where your finger is, but it ain't. Okay? But anyhow, that's it won't be on the test. It's not on the test. But just want you guys to know some of these strange things that Mother Nature, some of these tricks she plays on us. Okay. Oh, here, I did have that in here anyway. There it is. The scale reading will change. It will. You put your finger in the water, believe me, it's going to change, and that's a fun thing to do. We'll have to do that in the lab. Let's see. Archimedes first figured out the buoyant force is equal to the weight of the displaced fluid, and if the object is less dense than the density of the fluid, it will float. If it's more dense, it sinks, and if it's the same density, then you can put it anywhere and it will stay. Fish, as you probably know, have a way of adjusting their buoyancy by either increasing, well, there are a couple of ways they can do it. The most common way, though, is many fish have what they call an air bladder inside, and they can take air out of their gills and their blood and get it into that air bladder and make themselves lighter, or they can get rid of some of that air and make themselves heavier, so that when they're in neutral in the water, they can either go down by making themselves heavier or go up by making themselves lighter, and then they can swim around and get food. And alligators do the same thing, but they do it by swallowing stones. Okay, they can increase their weight so that they will then sink. They can go to the bottom more easily. Divers do it with weights around their waist, right? If any of you guys scuba dive, you know what I'm talking about. Okay. Pascal, back to him. Here we go. Now, the other thing that Pascal came up with, which was really a clever thing, he said that any change in pressure that you make in a fluid is immediately transmitted throughout the fluid. And we see examples of this, like I was saying here, a tube of toothpaste. No matter where you squeeze this tube of toothpaste, you guys know if that's the opening, that's where it's going to come out, right? It's going to. But that's because the pressure that's in here is the same. Or if you have barbecue sauce, you know, you go to Rib City or someplace like that, and if you have the kind of a squeeze bottle and you can squeeze out the ketchup or the barbecue sauce, what you're doing is you're creating a pressure in here, and what happens is that pressure is immediately transmitted everywhere throughout that liquid, and out it comes, okay? Because where the pressure has nothing to resist it, all right, it will flow out. But that was an important principle that he came up with, and I'll tell you why. If you've ever, well, you have, of course, had your car worked on, you guys know the way these lifts work. You know, I remember when many years ago, I remember watching them lift up my car on the lift, and he was doing it with air pressure over on the side. You know, this air. I said, how much pressure is there? He said, oh, I don't know, about 100 pounds or 150 pounds. I said, you telling me 150 pounds of pressure, and you're lifting up a 4,000 pound car? You know, he said, yeah. He said, I don't know why, but that's how it works. Well, here's why. Because of Pascal. you have a closed system here of a fluid, all right, a hydraulic fluid or oil of some kind, a thick fluid, and what you'll have is a small piston pushing on the fluid here and a larger piston underneath the car. All right, usually it's about this big, right, that inner part that pushes up. Well, the thing is the pressure is the same. And remember, the pressure is the force divided by the area. So in this case, you know, you've got 100 pounds of force, but it's on a little bitty area. So this gives you one number. I gave an example here. 100 pounds of force over, let's say, 1 square inch. All right? Now that's going to then equal it. See, this number is now 100 to 1. Right? That means that that's what the pressure is. That's what the pressure has to be here. 100 to 1. But in this case, since you've now got a larger, 50 square inches, now that 100 to 1 allows you to lift up 5,000 pounds. So that's how that works. But it was Pascal that figured that out, about the pressure being transmitted throughout the fluid. Isn't that cool? That's all he did. The pressure is the force over the area. And so if I give you a question like that in the test, you guys can do that? Okay, good. Let's see. All right, a bar of soap floats in the water, and it floats so it's level with the water. That's a lab I'd like to do with you guys, but they don't have all the stuff here for it. But in the high school, I have a lab where I have little plastic cups. They're actually caps for in plumbing. A plastic cap is what they are, an end cap. But the thing is, I get this little cup, and I have the students put that in the water. And of course, it floats in the water, about that much sticking up. And then I tell them, now, I want you to weigh out enough sand so that when you put the sand in there, it will make it float straight across, like in that picture there, straight across. And you can do it. It's actually a fun lab to do. It's not hard to do, really. It just takes a little time to figure out. Remember, if the bar of soap, they're giving you the volume here of the bar of soap, right? Or in that case, they have this little round container, and they can figure pi r squared h. They can figure out the volume of that container, and to have it sit level in the water, right, you can figure out exactly how much buoyant force you're going to need. So in this case, if the dimensions on the soap bar are 9 by 6 by 3, all right, you multiply those things together, and that will give you a volume, centimeters cubed, and then that centimeters cubed, all right, that volume multiplied by the density of water, which in that unit is 1, that's what the buoyant force is. Whatever, I don't know what the number is, 654, about 162, something like that. When you multiply that out, then that's going to be 162 units of force, you know, pushing it upward, the buoyant force, holding it up. But again, all you need to do there is figure out what is the volume that's underwater, which I think you have a problem in the homework that's like that. And then here, if your car is 1,200 kilograms and goes on a hydraulic lift, and this is the piston area, you guys should be able to do this. It's going to be, you can see here, I'll do it right here. It's going to be, remember, the pressure in one area, one location divided by the area at that location is going to equal the pressure in the other location multiplied by, divided rather by its area. So in this case it says, let's see, 1,200 kilograms is the car. So let's say 1,200, I'll do it like this, 1,200 kilograms. And on the other side, what do they tell you? The piston area under the car is 700. All right, and it says the, and then the input piston is 12. All right, and they say, so then how much force is needed to raise the car? So this is what you have to calculate. Actually, since this is kilograms, you have to multiply it by 10 to get force. So in this case, this would be 12,000 over here. Because I'm asking you for force. So 12,000 is going to be 7 into 120. I have no idea what that is. It's going to be 1.8 maybe, 7, maybe 1.9. multiplied by 12, whatever that number comes out to be, but then that would be your force here. But that's how you would do that. You guys see how you would set that up though? You just set it up like this and you can't go wrong. If I give you a problem like that, set it up like that and you'll be able to work that out. Okay? You're not in shock? You're okay? All right. Then gases, all right? Gas molecules, as it points out, they're far apart. You guys know all that. But this is where I was pointing out, about 20 miles. That's, you know, that's as thick as our atmosphere is. It's really very, very thin. I had a picture. I have to find that picture again. When somebody I know went up to the space station a few years, gosh, about 10 years ago now, but they went up there and they took a picture of the Earth, and I guess the sun must have just been, maybe have just gone down, you know, in terms of how it would look. But anyway, in that picture, you can see the thickness of the atmosphere in that, and you can really see how thin it is. It's really something that we need to be careful to protect. You know, things like the atmosphere, the water, and so forth. Well, look at the water. Look what's happening to you know, Lake Okeechobee and all the. You know, I mean, they don't have a choice with all the water. They've got to get rid of it somewhere. But look at the price that they're paying down here. Anyway, no politics. I'll stay out of that. Okay. Water pressure and air pressure. Just remember, as I said before, atmospheric pressure is just the weight of all those molecules pushing down on you. Just like when you dive into a pool, the weight of the water above you is going to give the additional pressure that you feel in your ears, because ordinarily you're at atmospheric pressure on the outside. Now, atmospheric pressure is going to be about, remember the force is about the, well, I'll just get down to the bottom line here, and that is the international unit for pressure is 1 Newton per meter squared. Now, a Newton is really a very small amount of force. There are almost 5 newtons to make up 1 pound. So it's a really, really small amount of force. And you know, a square meter is like a square yard. I mean, it's a big area. So this turns out to be a very tiny unit, the Pascal. So ordinarily you'll see it, the air pressure is about 100,000 pascals, or you'll see it written like this in your book, 100 kilopascals. Remember that lowercase k means 1,000. You have to multiply the number by 1,000 to get the number of the actual units of pressure. Okay, but that's the that's why when you look in the door of your car, you see the tire pressure. I should have looked at mine before I came in, but it's like my car is, I think it says something like 35 psi, pounds per square inch, and then next to it it says something like you know, 400 kilopascals, you know, of pressure. Instead of the psi, they use kilopascal. But you'll see that on your on the little label that's in the door frame of your car. But again, it's because the Pascal turns out to be such a tiny unit. Remember, we went through this with grams, how a gram, while it was very convenient for scientists to use for mass, it's the same mass as a dollar bill. I mean, it's just not practical. So that's why we had to go to the kilogram. Well, we do the same thing here. We go to the kilopascal. A barometer, I'll be showing you guys a film on that at some point here when I can get a DVD player, either here, hooked up here, or in the lab. And I want to show you the story about how the barometer came about. But in any case, the barometer came about by somebody taking a man, and actually it was in Rome, an investigator. He took a glass tube, sealed one end of it, filled it with mercury, put his finger over the end of it, turned it upside down, and then put the end of the tube and his finger in a dish of mercury. All right, he found that the mercury just fell a certain amount. Okay? And that he reasoned that what was happening was the air pressure pushing down on the mercury, just like it's pushing down on us, is what was holding up that amount of mercury in the tube. Okay, and that was correct. But in his day, he also knew that What was in the tube where the mercury was no longer there is a vacuum. And the Pope had said that there is no such thing as a vacuum. And so he knew he couldn't share this with anybody there. He's liable to end up dead very quickly. So what he did is he sent all this information off to Blaise Pascal, actually in France, through a couple of intermediaries, where it was far enough away from Rome that Pascal could investigate it, and then the politicians could take their time and get the Pope to say, oh yeah, there is such a thing as a vacuum, and then everybody would be happy. Because remember, back in those days, 500 years ago, the Roman Catholic Church ruled, Europe, so you had to be very careful. But you guys probably know that Galileo lived like in a prison. He had to stay in his house and on his property for a lot of his life because he said that the Earth goes around the sun. So Copernicus was right. People got in trouble for a lot of things back then. Anyway, so that's what this is all about. The weight of the mercury in the tube sticking up there, that height, is actually being held up by the pressure on the outside. And Blaise Pascal proved that. And in this little video that I will show you at some point, you'll see how that works. How do water pumps work? These old-fashioned water pumps. What they do is what they're doing is creating a vacuum up here, and they're pulling the water up through a tube, and then it comes out the end of the spigot. But it's because of it's because you are pulling the vacuum. This is like you sucking on a straw. Okay, the air pressure on the outside is what's pushing the water up through the tube. It's the same idea. Well, here, as a matter of fact, there it is. You drink through a straw. We say that we suck up this. Well, I guess that's true too. But ordinarily, what's happening is the air pressure is pushing down here, and you'll find that the liquid level is about the same, except due to some capillary action, it'll be about the same here. But when you lower the pressure here by sucking on the end of that straw, what's going to happen is that air pressure is now a lot greater, in other words, than the pressure in here, and then that allows the fluid to flow. And, okay, with gases, Boyle's law. Do you guys remember that from your chemistry? Right? Boyle's law, Charles' law. There are different laws about there, but Boyle's law is the one that I just want you to remember. He did his work at a constant temperature, and he found that the product of the pressure and the volume is constant, all right, in any closed system. So that means if you're going to cut the volume by 1/2, you're going to double the pressure, because this number has to be the same. You guys all see that? If that's got to be, right, if that number, here's the right, well, I can find it over here, I guess. Okay, let's say if the pressure times the volume under one set of conditions equals the pressure times the volume under another set of conditions. I want you guys to realize, let's say the pressure was 10 and the volume was 10. All right, now we have 100 on this side. All right, and now if you were to take the pressure and double the pressure, so now it's 20. You guys see what has to happen for this to be 100? Is this now has to drop to 5. All right, you see that, how it's related that way, that if you're going to double one, you cut the other one in half, or and vice versa. Okay, what they're saying is the product of these two has to stay the same, and that's Boyle's law for gases. And it's the same idea here. If you squeeze a balloon to half of its original size, what happens to the pressure? Well, obviously, as you guys can see, just like I did on the board here, it's the original pressure times the original volume has to equal the new pressure times the new volume. So that's how you can figure that out. You guys can do this? If I ask you something like this, you can do this? Bernoulli. I think this is the last one. But Bernoulli, he was a guy who figured out that if you have water flowing through, he just happened to use water, but water flowing through a pipe, that he knows that the pressure is going to drop. Well, you guys know that. If you have a hose and you turn the spigot on, then where the spigot is, you're going to have something like 50 psi or 40 psi here in Fort Myers, pushing that water through the hose. All right, and as it does that, If you have the other end of the hose open, the water comes out at atmospheric pressure, which is, compared to the faucet, that's 0. All right? So the pressure in the hose is going to be dropping from the 50 down to 0. Well, Bernoulli attached these little tubes to a larger tube just to show that the pressure will drop to 0 as you go along. But what he then said was, well, wait a minute, what if I make a constriction here, so that, what happens to the pressure, which he didn't know at the time, but he said, here's the deal. I know that the fluid is incompressible, okay? It's got to stay the same density, all right, all the time. And so if I'm putting, a gallon per minute through here, that gallon per minute has to go through the larger diameter and the smaller diameter, which means it's going to be traveling faster, right, through the smaller diameter to keep the gallon per minute, right, going through. Does that make sense? Right, that makes sense? Okay, so what he found when he did that was, though, that the pressure then dropped pretty severely at that, because as the fluid level picked up, as I said here, the higher flow rate of the smaller diameter, that resulted in a decrease of pressure in the fluid. And this has a lot of ramifications for the things that we do today, the world around us today. And I just have a few examples here, but this is why you can throw a curved ball in baseball, okay? Because if the ball's going this way, the wind is blowing on the ball. But if the ball is also spinning, I want you to realize that the air is going faster on this side than it is on that side, because the ball is spinning, and it's going to lower the pressure here and cause the ball to change its course. Okay? Airplane wings are designed, they're designed very carefully. Those wings have a very specific surface area, and shape to them. It's very important. This is why like now, up north, all right, when they have snow and ice, they have to make sure that the ice and snow stays off those wings. Because, well, you guys probably don't remember, but maybe 20, 25 years ago, they had an airplane take off at Washington National Airport, Reagan Airport it's called now, and it took off and they had a thin layer of ice on the wings. The guy couldn't get up in the air, crashed into the river there. And a lot of people lost their lives on that. They had to get out and in the freezing water, get out and get to shore. But the thing was, all you have to do is change the thickness of that wing a little bit, and it changes the aerodynamics completely. So, but the way these wings work is that the air over the top has to move faster. It goes a longer distance than the air on the bottom, and that makes the air that's going faster here create a lower pressure, which gives you the lift on the wings of the airplane. This is one where we don't have any sinks in here, but at home, when you guys, you go in the kitchen, or you go in the bathroom, you turn on the faucet, all right? The water that comes out, all right? Crank it on, all right? Does the water come out in a stream that spatters all over the place, or does it come out all soft and foamy, all right? What do you think?
Soft.
It comes out nice and soft, right? That's because of Bernoulli. See? We're in the lab the next time. You guys, you can just try with the faucet there. I don't think it has the attachment on it that your faucets all do at home. They have a little thing that's screwed into the end of the faucet, like this, that has slots in it, little slots that go around the periphery, so that as the water goes through, now you can make the water go very slowly and it will just come out as a steady stream. But if you turn the faucet on, what's going to happen is that water going through there is going to create, the speed of that water creates a lower pressure on the outside of the water that sucks air in through those little slots and makes all those bubbles that you get. So it makes it nice and soft, and you don't get spattered when you turn on the faucet. But again, that's Bernoulli. Oh, I forgot to bring this. I have to bring that the next time. A little funnel that you can blow on put a ping pong ball in there, and the ping pong ball, as long as I can keep going, okay, the ball will stay right here. It won't fall, it won't drop. But that's because the air going around the ball is going fast and it's creating a negative pressure there. Why do roofs blow off houses down here? Well, I can tell you that right away. Inside here is atmospheric pressure. outside here, with that wind blowing across the roof, lower pressure, up comes the roof, which is why our code calls for 2 ways of fastening a roof to a house these days. You need to do not just nail it, but you have to nail it and strap it. Any of you that do construction, you've got to know that. What else? Let's see. How about, let me see. Take a homework maybe. Here. All right, here's this piece of paper. Now, it's just laying there. But when I blow across the top of this paper, I'll be doing what to the pressure over the paper? Right? If I blow across the top, as opposed to down here, right? How about that? It went up. You never would have thought that ordinarily, right? You what? You know, but it's the lower pressure of the air moving here that's causing it to lift up. That's Bernoulli again. It's so many, these guys, you know, when they come up with something scientifically, and then the engineers get their hands on it, it can create look at today, look at your cell phones, you know, starting with a transistor. You know, you go to microprocessors, and, you know, the engineers take over and create all kinds of wonderful things. Oh, here, this was an example of that, so I didn't realize I had that in there, but that's, you guys, again, it's Bernoulli that allows allows what happened with the paper here, allows why the roofs blow off of houses. And again, the baseball spinning in the air. This is why back at the turn of the last century, around 1900, baseball was new. The umpires had to be very careful because the pitchers, you know, they had the ball in their, you know, in their glove, and they'd be standing out on the mound there. Sometimes they would bring in a little piece of sandpaper, you know, and hide it in their glove. And then they would rough up the outside of the ball a little bit, just a little bit rougher, because with the ball a little bit rougher, it gives it a lot more action as it's going, because it pulls more air with it as it rotates, as it goes through the air. So the umpires, to this day, they still look at these balls and make sure that they don't have any marks on them or of any kind. Okay, but anyway, this talks about the faucet, the airplane. Okay, we've already gone over all that. You might notice if you have a stream of water that's falling, again, the initial speed of the water will give you a certain size, but as the water falls and goes faster and faster, then as the speed increases, the diameter will get smaller and smaller due to the lower pressure, and that again, it's Bernoulli. You know, he's just all over the place. Here's one. And by the way, I'm pronouncing that wrong. I had a student tell me a couple of years ago, a French student, that you pronounce that Poisserie, but I looked up I Googled it the other day, and no, it's not. If you're French in here, you can probably tell me. It's something like Poisserie, but it's not, they don't pronounce it the same way. I don't know how you guys, who are CBT people, how you guys would pronounce it, but how do you say it?
Pastellis. Okay,
well, there you go. It sounds Italian now, okay. Sounds like Pacelli's Pizza. Yeah. Okay, but in any case, he came up with an important relationship in terms of flow, talking about how he has a whole bunch of constants here, which we'll ignore, but the main thing is that the flow rate through a tube is going to depend on how much pressure difference there is as you go from one end to the other. It's going to depend on the radius of that tube to the fourth power. How these guys figure this stuff out, I have no idea. And divided by the length. The longer the tube, the slower the flow rate will be. So I just wanted to put down here, if you double the length, you'll lower the flow rate by 1/2. If you double the pressure, you increase the flow rate by a factor of 2. But if you double the radius, you're going to increase the flow rate by a factor of 16. Okay, this is really important because I know you guys who work in the cath lab, you know, you're looking at how much of a, you know, how much of an occlusion, you know, is in a, lower interior descending artery or something, and you guys will look at a picture and see, and try and see what the size is. Based on that size, you can see how the flow rate will get a lot smaller, and this is why the physician will say to the patient, you know, you're 85% occluded, you know, in that particular artery. You need to go in and get it back to its normal diameter. But again, it's this equation that does that. And there's one more, let's see. This is one that Bob Clements told me to make sure to go over with you guys about Laplace's law, which just says that the wall tension, that is the pressure that's inside the wall itself, all right, it is related to the actual pressure of the fluid multiplied by the radius. So I want you to realize that that tension in the wall, all right, is going to get bigger if the internal pressure can stay the same. But if the radius gets bigger, like if you have an aneurysm and the radius gets bigger, even though the pressure may still just be 120 millimeters of mercury, now that you have a bigger radius here, you have a lot more pressure on the in the walls, on the walls of the aorta, and so you have much greater tension there. Does this make sense? You guys figure this out? If I ask you this on the test, you're okay with this? Explain this? All right. But that's how, when I was selling these arterial grafts, this is one of the reasons that the FDA said, told us and the other manufacturers, we want you to follow these patients and look at their graft at least every 5 years. Take a look at it, because some people, not all, but some people have enzymes in their blood that will dissolve dacron, all right, very slowly. But so the FDA always wanted us to watch it to make sure it wasn't beginning to dilate because of the knitted or the woven dacron getting weaker and expanding according to Laplace's law here. And that would, of course, mean the patient would have to have it replaced before it bursts, just like the original aorta would. There's, well, before we get to that, there's one other equation I wanted to go over with you guys, and that is, because if, here it is on page, looks like it's on page 165. It's when they're talking about renewing. It's the equation of continuity, it's called. Did you know, if I was talking about a hose, you hook the hose up to the faucet, okay, and so let's say water's just coming out, okay, like we talked about before. And I suppose I want to spray somebody back there. What do you do to the hose to spray somebody further away? You're going to cut down the area, right? When you cut down the area, you're going to pick up the speed of the water. And that's the equation of continuity that you guys have on page 165. So it looks like this. It just says that the area that the water is going through multiplied by the speed of the water at that time is going to equal the area, if you change the area, and multiplied by the new speed, just like we did before with Boyle's law. And your book has this on, as I say, on page 165. But I want you to realize what you're doing is you have one area and one speed, and that's fine. And then suddenly you make this area a lot smaller. What you're going to have to do here is pick up that speed a lot, okay, in order to keep the number the same. For example, let's say the area was 10. 10 units in area, and let's say the speed was 10, all right, you can see now this is going to be, the product's going to be 100, but then again, if you make that area, if you go from 10 and make that 1, look what has to happen to the speed. In order to keep this number to be 100, the speed is going to have to go to 100. You guys see that? And of course the opposite is true too, if you make the areas larger. Okay, but that's why you can spray somebody when they're further away. It's just because you can, and fire hoses work the same way. They have nozzles that they can get to make it smaller or larger, depending on a particular window or something they may need to get the water in. Anyhow. And then lastly, I think this is last, isn't it? Yeah, there we go. I just wanted to point out to you, you don't have to know any of this, but for Chapter 7, I just wanted you to get familiar with some of the pressures that are normal in the body. The pressure in the eye, 10 to 15 millimeters. But you guys would know that if you go and get checked for your eyes checked, at lens crafters, or you go to a physician's office, optometrist's office, right? They can either put a little scale right on your eye, or they can use the little shot of air, right, to do it. But anyway, your number should be in that neighborhood, 10, 15. I know they don't want it over 20. And then urinary bladder pressure, it depends on, when you notice it. Like all of you are probably at least 25 millimeters of mercury now, right? you're ready to go pee. But the thing is, the pressure in the bladder will increase anywhere from, from 25, and you'll notice it, anywhere from 25 to roughly 100 millimeters of mercury. Fortunately, we can also override it, which is nice. Sometimes you can just say, chill, and you can wait it out for a while. Cerebrospinal fluid pressure, that's going to be related to Pascal. When they do a spinal tap and they want to know what the pressure is, say in the cranium, what do? They have to calculate what the pressure is down here where they tapped, okay, just because of the height, and they have to subtract that from the actual pressure that they're reading in order to get what the pressure was up here. So they're using Pascal again there. Red blood cells, I think you guys know, if you're in a hypertonic solution, then what happens is there's a lot of hypertonic, you'll have a lot of salt in the water, and what will happen is then the water will come out of the red cell to try and dilute the outside, and it causes the cell to crenate, or crumble up. And the opposite is true if you put it in a solution where there's less salt than you have in the cytoplasm of the cell, and in that case it will expand, it'll suck water in until it bursts itself. In hemodialysis, what we're doing is removing salts and other metabolites through a semi-permeable membrane. In hemodialysis, you have to be sure that on one side of the membrane you'll have blood, and on the other side you'll have the salt solution. You want to have the right amount of sodium and chlorine and phosphate and the things that you need in the blood. You want to have that in the salt solution too, so that whatever gets transferred will be equalized on both sides. On the other hand, you want to get the urea, creatinine, and other products. You want to have none of that on the water side, the salt side, so that they will go through the membrane. And the fusion rate is related to temperature and the difference in concentration. But I think you guys know that if I brought in a hot pizza here and sat it down, you'd know that in a matter of a couple of minutes you'd be able to smell that anywhere in the room, because the molecules that make up the aroma from that are hot, all right, and they're also diffusing through the rest of the air. And that's all. All right, can we go home now? Now, when you work on these problems, you can either, if you want to physically get together to go over them, please let's do it right after we do the lab, or whatever lab we're going to do on Wednesday. And those of you that don't have a lab on Thursday, please email me and I'll explain to you how to do any of the problems that you're having trouble with, okay, on campus. Yes?
You also told us after lab last week you cut out 2 of the problems.
Yeah, oh yeah, well, that's true. Which ones are they?
19 and 21.
Thank you, yes, that's true. We did, we skipped section 6.4, which is from 1921, is that 32? Yeah, just drop those. Okay, but the other ones are the same. Okay, so drop 19 and 21, please. Yeah, don't do that.
Are you going to stand back on the Wednesday or
I'll do it now. No, I really would just as soon do it now. It'll take me a few minutes, but I'll be glad to, for sure. All right, hold my eyes.